Alright, so my name is Haynes and this is Lab 5, the motion of falling objects. The observation that we're making is that we're going to observe one object dropping fast, which I chose to be a toy ball, and one object dropping slow, which is a paper towel folded up. And the analysis of, we're going to analyze the motion of both the objects and compare their speeds and accelerations and how they are affected by gravity and the force of drag. And the main result is that while both objects are affected equally by gravity, and by gravity I mean the force of gravity, 9.81 meters per second, then the slower falling object is more affected by the viscous drag force, which causes it to move more slowly when it falls. So we'll go to tracker, and so for the fast moving ball we'll look at first. My origin is in the center of the ball, and it's going to move in the negative y direction, and the scale that I chose is the length of the ball. So if we run that, you can see it accelerates, and here are some important initial conditions. We have the fast moving ball, which is the delta T is about 0.6 seconds for that. It's about 416 grams. And so now we'll look at the slow moving object. Again, the origin is in the center. The delta T is a little bit longer for this one. It's 1 second instead of 0.6 seconds. And the mass is a little smaller. It's 10.5 grams. And if we drop it, you'll see that it moves a little bit in the x direction. I'll show you the coordinate system. The scale is the length of the paper towel. It moves in the x direction, but that shouldn't affect the y direction because the y direction of force and the x direction of force are independent, so that shouldn't make a difference. Okay, so now that we've tracked our objects in Tracker, we can run our simulation. So our first simulation that we're going to run is the fast object with gravity only. So you can see our gravity is, it's only predicting the force of gravity, so we'll run that module. And you can see that it accelerates, but if we look at the graph, the observations do not go with the simulation. We need to include the force of drag. So if we include the force of drag, which is right here, and we run that module, you can see that the data lines up a lot more. So we have the tracker model fitting, or the tracker observations fitting more with the simulation. And so now we'll do the same thing with the slow object. So our slow object with gravity only, we'll run that module. There we go. And you can see again, tracker is not lining up with the simulation. It definitely levels out a lot more where the simulation accelerates. So if we include the slow object drag, also notice that the drag force of our object is greater. So again, we have the drag included. F net is F grav plus F drag, and we'll run that module. And we can see from our graph right here, you can see from our graph that it lines up more with our tracker observations. So now we can ask our what if and what does it mean question. So what does it mean? Well, looking at the slow object, we can see that with the adjusted drag force, the object reaches terminal velocity pretty quickly. This means that the drag or upward force was great enough to cancel out the force of gravity, causing the net force to be 0 and the object moving at constant velocity. So in the graph with gravity only, the object is accelerating as indicated by the exponential decline of the simulation graph, but in the graph with both gravity and drag, the path of the line becomes more straight and linear, which we can indicate as a constant velocity. So the objects do both actually hit terminal velocity. So now we can ask, what if we had an initial downward velocity? So we can go ahead and test that in Tracker, and we can make our ball velocity. We're using the slow object gravity and drag code. So we'll make our ball velocity, let's say, -1 meters per second. So we can run that module. Yes. And we can see that the line is almost entirely linear the whole way through. And that's because the object reaches a terminal velocity really even quicker, because the object is already moving fast enough with the downward force to be canceled out by the upward force. So if we have an initial downward velocity, the object reaches terminal velocity even sooner. So thank you for listening to my lab report.